In this final video of this DVD, I wanted to discuss just a few more trigonometric identities that I personally think are fundamental knowledge if you wish to study trigonometry further on your own. These identities are called compound angle identities because they describe what happens if we find the sine or cosine of the sum of two angles. That is to say, we add two angles together and then find the sine or cosine of the resultant angle. So if we had two angles, for example, we had theta and we had beta, what we're saying is we're finding the sine of theta plus beta, or the cosine of theta plus beta. Now hopefully it goes without saying that the sine of theta plus beta does not equal the sine of theta plus the sine of beta. We can quite clearly see this if we were to assign example values to theta and beta and work out what the sine of theta plus beta equals and work out what the sine of theta plus the sine of beta equals. So if we were to say that theta equals 30 degrees and beta equals 40 degrees, well then the sine of 30 degrees plus the sine of 40 degrees is equal to, we can use a calculator to work this out, so the sine of 30 degrees plus the sine of 40 degrees is equal to 1.14. Well, we can clearly see this can't possibly be equal to the sine of theta plus beta because this value is outside of the range of what the sine function can return. The sine function can only return values between -1 and +1. This is greater than +1, so it can't possibly equal the sine of theta plus beta. Just to prove that further, we can actually find the sine of 30 degrees plus 40 degrees, which is equal to the sine of 70 degrees, which equals, again, if I use a calculator, so 70 sine is equal to 0.9396, or 0.94, I guess we could say. So it's equal to 0.94. We can quite clearly see that 1.14 does not equal 0.94, and therefore sine of theta plus beta does not equal the sine of theta plus the sine of beta. Now I'm not going to show it here, but the same is true for cosine. The cosine of theta plus beta does not equal the cosine of theta plus the cosine of beta. So what does the sine of theta plus beta equal, and what does the cosine of theta plus beta equal? Well, we can construct some geometry to help us answer this question. By applying trigonometry to that geometry, we're able to find relationships between these angles and find what the sine of both of those angles or the cosine of both of those angles are equal to. Now, it is quite a complicated proof, so please bear with me, but hopefully everything will make sense in the end, even if you can't see where I'm going with this to begin with. So just sit back, watch through the proof, just make sure you understand why certain things equal the whatever values I'm saying they're equal to, but don't worry where I'm going with this proof. Just sit back, watch the proof, and hopefully in the end you'll see how everything comes together and finds us what sine of theta plus beta equals and what the cosine of theta plus beta equals. So I'm going to start out by giving myself as much room as possible here on the whiteboard, and I'd like to draw a horizontal line. So I'm going to draw a nice horizontal line. Now if we took this line and I was to rotate it through an angle of theta, we'd get something like this. So if I rotated this line up and through an angle of theta, we'd see we have these two lines and the angle between these two lines would be theta. If I took the line again and rotated it through an angle of beta, you'd see that we'd take the line again and rotate it through an angle of beta, and I'd get something that looks a little bit like this. I'd have another angle here, and this angle would be beta. So hopefully you can see that we know the angle theta, we know the angle beta, and if we were to construct some geometry now that allowed us to work out various relationships between these two, perhaps we can find out the relationship of the sine of theta plus beta and cosine of theta plus beta. Now we're going to start off looking for the sine of theta plus beta. To do this, I want to first call the shared point, this point that all lines share, O. or sort of like the origin, if you will, of our drawing. I'm going to call this O. I'm going to create another point on our third line that's called P. So here's a point P. Now the important part here is that the line OP has a length of 1 unit. So this line between O and P is 1 unit long. We can now define a right-angled triangle such that this new line, OP, is the hypotenuse, and that one of the points of the right-angled triangle is on the second line that we created. So I'm going to construct a right-angled triangle, and that needs to meet this second line at a right angle. And the point where it meets that line, I'm going to name as Q. So it meets this line at a point Q. Now we can apply trigonometry to this right-angled triangle to relate our angle beta to the various edges in this triangle. So the first thing we know, well, the sine of beta is equal to the opposite over the hypotenuse. Well, the opposite is PQ, so it's equal to the edge PQ divided by the hypotenuse, which we know has a length of 1. So really we can see that the sine of beta is equal to PQ, or more useful for us is to know that PQ is equal to the sine of beta. We can find the cosine of beta. We know that's equal to the adjacent over the hypotenuse. Well, the adjacent to beta is OQ, and the hypotenuse again has a length of 1. So if we were to divide this by 1, well, that just becomes OQ. So we can see the cosine of beta equals OQ, which again is going to be more useful for us to have written as OQ is equal to the cosine of beta. Both of these facts, the fact that PQ is equal to the sine of beta and OQ is equal to the cosine of beta, they're the two edges here in our right-angled triangle. Both of those facts are going to be useful to recall later on. So moving on, we can construct another right-angled triangle, but this time relating to theta instead of beta. So I'm going to share the point Q that we've already created, and I'm going to drop a line down from Q so that it meets that original horizontal line at a right angle. Now the point where these two lines meet I'm going to name as A, and we can apply trigonometry to this triangle relating to angle theta, much like we applied trigonometry to our original right-angled triangle. Now in this case we're going to see we only need to find the length of QA, we don't need to find the length of OA, and because of that I'm only going to use the sine trigonometric ratio. So we know that the sine of an angle, so the sine of this case of theta, is equal to the opposite over the hypotenuse. Well, the opposite is the edge AQ, and the hypotenuse is the edge OQ. But we know, of course, that OQ is equal to the cosine of beta. So the sine of theta is equal to AQ divided by the cosine of beta. We can rewrite this to find AQ is equal to, if we multiply both sides by the cosine of beta, it's equal to the sine of theta times the cosine of beta. So I'm going to write this up here as we're finding the lengths of various edges in our diagram. So AQ is equal to the sine of theta times the cosine of beta. I am going to erase the rest of our workings so we keep this as clean as possible and we keep only the information that we need to remember on our whiteboard, because otherwise we're going to be overrun by all the workings and we're not going to be able to see which workings are important to us. So I'm just going to erase this. Alright, so we're getting started, we're constructing some geometry and we're finding relationships between this geometry and our two angles. But how is this helping us find the sine of theta plus beta? Well, we've seen in both cases with both of our right-angled triangles that the sine relates our hypotenuse to the opposite edge. So if we wish to find the sine of theta plus beta, we need to construct some opposite edge for those two angles that creates a right-angled triangle where the angle that we apply the sine ratio to is both of these angles added together. That is to say, this line here is going to be the base of our triangle, Our line here would be the hypotenuse of our triangle, and we need to construct some opposite edge so that we can find the sine of both of these angles as being some relation of this edge. Now, if we make the point P part of our triangle so that the hypotenuse is OP, which we know has a length of 1, that's actually going to make our life a lot easier for us. So what I can do, I know this is a perfectly horizontal edge, so if I was to construct a perfectly vertical edge that drops down to it from point P, we know that it meets at a right angle, and we'll notice, as I bring a layer that I can draw on, I am going to name this new point as B. You'll notice here in this right angled triangle, we have the hypotenuse as a length of 1, and the opposite edge is this edge BP, or PB. Therefore, we know the sine of theta plus beta is equal to the opposite, which is PB, divided by our hypotenuse. Our hypotenuse is OP, which we know has a length of 1. Therefore, we know the sine of theta plus beta is equal to PB. Now, why is this useful for us? Well, if we can find the length of PB, if we can find the length of this newly created edge right here, then we can find the sine of theta and beta. What we need to do is we need to find the length of this in terms of things that we know. All we know are these angles, or of course we can apply trigonometric functions to these angles. So we're attempting to find the length of PB in terms of theta, beta, or the cosine and sine of those angles. To help us find the length of PB, I'm going to break this line down into two different sections. Now, we already know the length of AQ. We know that that's equal to sine theta cos beta. So what if I was to create a section on PB that was the same length as AQ? That would then leave us only needing to find the length of the remaining section. So allow me to create a horizontal line from Q over to the line PB. We know that that will meet that line at a right angle because effectively the line, as I bring up a layer I can draw on, there we go, this new line that we've created is parallel to the line BA. And because it's parallel to BA and because PB and AQ are parallel to each other, we know we've effectively just defined a rectangle here. So I'm going to call this new point R, and we know that BR is the same as AQ. So because of that, and I'm actually going to call this RB just to keep with the notes that I've got over here. So because of that, we know that RB is equal to AQ. They are the same length. This is a rectangle. Notice that we've got right angles here in all of the corners. So this is a rectangle, and because it's equal to AQ, we know it's equal to sine theta cosine of beta. So now that we've found the length of RB, all we need to do is find the length of PR. We can add those together, and that's going to give us the sine of theta plus beta, because it's going to give us PB. Now notice we've actually constructed a right angled triangle here. The triangle PRQ is a right angled triangle. Therefore, if we can find either of these two angles other than the right angle in that triangle, we can apply trigonometry to this triangle to find the length of PR. Luckily for us, we've also created a line that intersects two parallel lines. It may not be very clear, but we do actually have that scenario, because OA is parallel to RQ. We can see this because RQ and BA are both perpendicular to the line PB. So if they're both perpendicular to the same line, then these must both be parallel. And we know that BA is just a section of OA. So if BA is a section of OA, then OA is parallel to BA, which means it's also parallel to RQ. So OA is parallel to RQ, and we can see the line OQ is intersecting both of them. So we have a scenario where we have two parallel lines and a line intersecting them. Now in Volume 1 we discussed Euclid's theory on such a scenario, and that allows us to relate certain angles to others. Now this may be a little bit confusing to follow, so I'm going to try and work through it slowly, but we can see in such a scenario where we have a line intersecting two parallel lines, if we had an angle here, which I'm going to name this angle theta, well, it told us that this angle is also theta, the angle up here is theta, and this angle down here is also theta. Well, notice in our scenario here where we have OA and RQ being intersected, in that scenario, the angle right here is this angle theta. And notice, the angle in here would be this angle right here, which is also theta. So the angle between R, Q and O is theta, and we know theta, it's a known value. We know theta, we know beta. So if we know theta, then perhaps we can use this to somehow work out the angles in this right-angled triangle. Well, look, we have a straight line here, and we can see that there are three angles that add together to form the angles on this straight line, which we know are 180 degrees. Those three angles are a right angle of 90 degrees, plus some unknown angle, which we can call x, plus theta. So we have some unknown angle in here, which I'm going to call x, and that is going to be equal to something. What is it equal to? Well, if we subtract 90 degrees from both sides, we can see that 90 degrees is equal to x plus theta. Then if I was to subtract theta from both sides, we can see that 90 degrees minus theta is equal to x. So this makes sense, because if this is 90 degrees and the whole thing is 180 degrees, well then this portion here must be 90 degrees. And if that's 90 degrees and this is theta, this must be 90 degrees minus theta. So x is equal to 90 degrees minus theta. I'm going to leave that there just for a second because it's going to be useful to us shortly. So x is equal to 90 degrees minus theta, and I can get rid of theta here as well, so we keep our diagram as clean as possible. But that's not necessarily going to give us the nicest end results. I mean, 90 degrees minus theta sure could be useful, but it's not going to give us the nicest end result. So what else can we find about this particular triangle? Well, we know these three angles must add to 180 degrees. So again, we have 180 degrees is equal to, well, a right angle, 90, plus x, well, we know x is 90 degrees minus theta, plus some other angle that we don't know. Well, let's call that angle y. So I no longer need to know the value of x. We've used that, and I can erase that. Fantastic. So let's rearrange this to find what angle y is. Well, 180 degrees is equal to 90 plus 90 is 180. Minus theta plus y. Well, if I take 180 from both sides, it's clear that they're going to cancel. So 0 is equal to minus theta plus y. And then if I added theta to both sides, we get theta is equal to y. So y is equal to theta. This is a value that we know, and it's a nice clean value. So if I was to erase y, we actually know that this angle right here is equal to theta. So once again, allow me to clear the workings that we no longer need from our whiteboard. I want to keep this as clean as possible. But now that we know that that angle is theta, we can apply trigonometry to our geometry here, to that triangle PQR, to hopefully find the length of PR. So if we're interested in finding the length of PR, we know that in relation to our angle, PR is the adjacent edge. Now we don't know the length of RQ, but we do know the length of PQ. We know PQ is equal to sine of beta. Therefore, we know PR, the adjacent, and we know PQ, which in this right-angled triangle is the hypotenuse. So we know the adjacent and we know the hypotenuse. So therefore, we can say the cosine of theta in this case is equal to the adjacent, PR, divided by the hypotenuse. The hypotenuse is PQ, which we know is sine beta. So we can rearrange this to find the length of PR. We can do that by multiplying both sides by sine beta. That tells us that PR is equal to the cosine of theta times the sine of beta. So I'm going to write that in here. PR is equal to the cosine of theta times the sine of beta. Again, I'm going to erase any workings that we don't need, just to keep things as clean as possible. But now that we've found the length of PR and we already knew the length of RB, we can now add those together to find the total length of PB. Again, we found the length of PR, we already knew the length of RB, we can add those together to find the total length of PB. And why are we doing that? Because PB is equal to the sine of theta plus beta. So PB is equal to, well, it's going to be equal to RB plus PR. It's equal to this part of our line plus this part of our line. So it's equal to RB plus PR, which is equal to, well, RB is equal to sine of theta cos of beta. So it's equal to the sine of theta times the cosine of beta, plus PR is the cosine of theta times the sine of beta. Now, once again, what did we say about PB? Well, PB is equal to the sine of theta plus beta. So the sine of theta plus beta is equal to the sine of theta times the cosine of beta plus the cosine of theta times the sine of beta. We have found the sine of theta plus beta in terms of only values that we know. It's in terms of theta and beta, or of course we can always calculate the trigonometric functions of an angle. So we have found the sine of theta plus beta in terms of things that we know. And this is the first of our compound angle identities. Now don't worry, the others are actually going to be a lot quicker to derive now that we've done all of this groundwork. The second compound angle identity I wish to derive is the sine of theta minus beta. Now to do this, we can simply use our sine of theta plus beta, but make angle beta equal to negative beta. So we can say sine of theta minus beta is equal to the sine of theta plus minus beta. If we take that and use minus beta for each of these angles, we're going to get that the sine of theta minus beta is equal to the sine of theta times the cosine of minus beta plus the cosine of theta times the sine of minus beta. Now we saw in the previous video that the sine of minus theta is equal to the minus sine of theta, and that the cosine of minus theta is equal to the cosine of theta. Therefore, the cosine of minus beta is simply the cosine of beta, but the sine of minus beta is equal to minus sine of beta. So this is going to be a minus multiplied by the sine of beta, which is the same as having minus multiplied by cosine of theta sine of beta. Since we're simply multiplying minus 1, it doesn't matter where that minus 1 comes in. And we know, of course, therefore, this is the same as saying minus the cosine of theta sine of beta. So again, we had cosine of theta sine of minus beta, but the sine of minus beta becomes the negative sine of beta. If we had a negative multiplied by the sine of beta and all of that multiplied by the cosine of theta, is the same as having a negative multiplied by the cosine of theta multiplied by the sine of beta. So therefore the sine of theta minus beta is equal to the sine of theta times the cosine of beta minus the cosine of theta times the sine of beta. So you'll notice from our two identities, there we go, that when it's sine of theta plus beta, we have sine theta cos beta plus cos theta sine beta. When it's sine of theta minus beta, the only difference is we have a minus here. We still have sine theta cos beta, but we subtract cos theta sine beta. So this is our second compound angle identity. Our third compound angle identity is going to be similar to the first, which was sine of theta plus beta, but for the cosine. So we're going to try and find the cosine of theta plus beta. To do this, I'm going to reuse our earlier diagram. I need to clear some room, so I'm going to erase some of the workings that we no longer require. So bear with me a second. We are going to be reusing our diagram, but we're going to be relating theta and beta using the cosine of theta plus beta rather than the sine. But you're going to notice, because we've done a lot of the groundwork, we've already drawn this diagram out already, this is going to be a lot quicker than when we found our sine of theta plus beta. So nearly there, just erasing some room so that we have as much room to work with as possible. Fantastic. So we are trying to find the cosine of theta plus beta. That's this angle right here, which means, of course, we're dealing with the right-angled triangle OBP. Now, in that triangle, we know the cosine of an angle is equal to the adjacent over the hypotenuse. Well, the adjacent edge is this edge OB. So it's equal to OB divided by the hypotenuse, which is OP, but that hypotenuse has a length of 1. So if we're dividing by 1, we know it's simply equal to OB. Well, what do we know about this edge OB? Well, we know that we could write this edge OB as OA minus BA. If we take the entire length OA and subtract back from it BA, it's going to give us the length OB. So this is equal to OA minus BA. But what else do we know? Well, we know that BA is the same length as RQ. We know this, it's a rectangle, therefore the two ends of the rectangle are equal length. So we know that this is also equal to OA minus RQ. So bear with me 1 second as I write this up here and then erase the rest of our workings. So the cosine of theta plus beta is equal to OA minus RQ. So that means if we can find the length of OA and we can find the length of RQ, we can find the cosine of theta plus beta. Well, OA, this length here, OA, can be found by analysing the triangle OQA. We know one of the angles in this triangle is theta. We know OA is adjacent to this angle. And we've also found OQ. We found OQ earlier as the cosine of beta. So we could use the ratio that relates our adjacent and hypotenuse, which we know is cosine, and say the cosine of theta is equal to, well, that's going to be equal to our adjacent, OA, divided by our hypotenuse, OQ. But we said earlier that OQ is equal to the cosine of beta. So our cosine of theta is equal to OA divided by the cosine of beta. That means OA is equal to the cosine of theta times the cosine of beta. So that's what OA is equal to. So allow me just quickly to erase this, just so we can keep everything all on one page. I don't have to scroll around. Fantastic. So OA is equal to the cosine of theta times the cosine of beta. So that's OA, but what about RQ? Well, RQ we can find by using the triangle PRQ. We know that RQ is the opposite edge of our angle theta, and we already found PQ. We know that PQ is equal to sine beta. So PQ is the hypotenuse of this triangle. RQ is the opposite edge. That means we can say the sine of theta is equal to the opposite, RQ, divided by our hypotenuse, and our hypotenuse is PQ, which we've already said is sine beta. So sine beta. That means that RQ is equal to sine theta times sine beta. So we know that OA is equal to the cosine of theta times the cosine of beta, and RQ is equal to the sine of theta times the sine of beta. That means the cosine of theta plus beta, which is equal to OA minus RQ, the cosine of theta plus beta, which is equal to OA cosine of theta cosine of beta minus RQ sine of theta sine of beta. So this is our third compound angle identity. The cosine of theta plus beta is equal to the cosine of theta times the cosine of beta minus the sine of theta times the sine of beta. Now the final identity for this video is going to be the cosine of theta minus beta. For this I am going to bring up a new whiteboard because I think we've pretty much pushed the limits of everything we can squeeze onto that board. So I'm going to bring up a new whiteboard. I'm going to start out by rewriting our third identity. So the cosine of theta plus beta is equal to the cosine of theta times the cosine of beta minus the sine of theta times the sine of beta. Fantastic. So the the final identity, fourth and final identity that I'd like to show in this video is the cosine of theta minus beta. Now we've seen we can use the cosine of theta plus minus beta to show this, just like we saw with sine. We simply make our angle equal to minus beta and then use our formula for the adding of two angles. This is going to give us the cosine of theta times the cosine of minus beta minus the sine of theta times the sine of minus beta. Now we've already seen that the cosine of a negative angle is simply the cosine of the positive angle. This is equal to the cosine of theta times the cosine of beta minus, well, the sine of a negative angle is equal to the minus sine of the positive angle. So all of this is going to get multiplied by a negative 1. So it's the same as minus sine of theta sine of positive beta, because this became minus sine of beta, and that minus can simply sit at the front of the entire multiplication. So these two minuses here are going to become a positive, because minus a minus number becomes a plus. So we have, as our fourth and final identity, that the cosine of theta plus beta is equal to the cosine of theta times the cosine of theta plus the sine of theta times the sine of beta. So just to recap, here are our four compound angle identities. The sine of theta plus beta is equal to the sine of theta times the cosine of beta plus the sine, actually let's write this the same way as we had before rather than switching the terms around, plus the cosine of theta times the sine of beta. The sine of theta minus beta is equal to the sine of theta times the cosine of beta minus the cosine of theta times the sine of beta. The cosine of theta plus beta is equal to the cosine of theta times the cosine of beta minus the sine of theta times the sine of beta. And finally, the cosine of theta minus beta is equal to the cosine of theta times the cosine, rather, as I attempted to write sine, the cosine of beta plus the sine of theta times the sine of beta.